All right, so let's look at solutions to simultaneous linear equations. Now we know how to solve equations where you have a solution, where we use the methods of substitution or we use the methods of elimination. However, we're not going to look at those today because we know how to do them. We're going to instead look at the context where you are asked something along the lines of finding particular values to show that something has no solutions, unique solutions, or infinite solutions. So before we can actually perform those and work through the questions, we actually need to understand what each one does, which one means. So firstly, when you hear a unique solution, it means that the two lines cross just the once. And you can see that in this first diagram here. You can see the blue line and the orange line are crossing each other just the once. They don't have to both be going that direction. You can have different directions if you want. That is perfectly fine. As long as they're crossing once, you have a unique solution. Now, in terms of properties of the graphs, remember linear equations can be written in the form y equals mx plus c. So each of these follows y equals mx plus c. For equations to have a unique solution, you must have different gradients. That's the only condition. You can clearly see different gradients here, and that means they cross over with each other once. Another case is no solutions, and that is where we have two parallel lines. So you've got the orange and the blue lines here. They're completely parallel. They're never going to cross. You have no intersection point, therefore no solution, because remember, the idea of intersection point means there is a solution. So no intersections, no solutions. The properties of y equals mx plus c, which must occur this time, it's clearly the gradients must be the same because the lines are parallel. So the gradients must be equal to each other. However, you can clearly see there must be different y-intercepts. So same gradient, different y-intercepts, and you'll end up with no solution. And the final case is when you have infinite solutions. It's where you've got essentially the two lines are exactly the same. They might look a bit different, but they're really the same line. So if I had something like y equals 2x plus 1 and 2y equals 4x plus 2. Those two lines look different in their equations, but really the bottom one is just a multiple of the top one. If I double the top one, multiply all this by 2, you will get the same thing. And as soon as that happens, you have the case with infinite equations. So they're exactly the same line. So you can see here you've got two lines exactly the same. So they have the same gradient, the same y-intercept. They're your three cases. Unique, different gradients. No solution, same gradient, different intercepts. 3, you've got infinite solutions with gradients and intercepts the same. So let's do a couple questions you might see in exams as in preparation for them. You've got your case 1 example, which is where you have the unique solution. So for these simultaneous equations, find the values of k, or values, they'll often be brackets because sometimes it can be more than one, that there is a unique solution for. So let's have a look at this. We've already said for this case, the gradients must be different, must not be the same. Now there are multiple ways to do this. You can use matrices, but at the moment that's no longer part of the Year 12 Methods course in 2020. So I'm going to show you how to do it by equating gradients. Not necessarily the quickest way, but it's within the course without introducing any extra methods that we haven't done at this point. So what I want to do, I'm going to label both of these equations. I'll call them equation 1 and equation 2. I'm going to rewrite them both as y equals mx plus c. So you have this equation here. And we're going to transpose it to get y by itself. So I'm going to leave the k minus 2 over there. Equals 5. And I'm going to subtract the 2x and then divide it by k minus 2. So it's 5 over k minus 2 minus 2 over k minus 2 times by x. And hopefully you can see that this value here is the gradient. Remember, the coefficient of x is always the gradient. That's our M1. The second case that we have, equation we have, let's rewrite this one. So you have 2kx plus 3y equals -5. And let's transpose this. So you have 3y equals -5, take 2kx, divide it by 3, gives you -5 over 3 minus 2k over 3x. And again, I'm going to highlight this one. That is the gradient of our second line, M2. So remember what we said about the case. The case example is the gradients cannot equal each other. So now I'm going to solve an inequality for the gradients not equal to each other. So we have -2 over k minus 2 equals -2k over 3. Now this is easily solved on a CAS calculator or something. We're doing this as though we haven't got a CAS. It doesn't matter, you can use a CAS from this point. But if I solve this equation, I need to multiply by 3. So you're going to have -6 equals -2k bracket k minus 2. This becomes a quadratic I need to expand out. So -6 equals -2k squared plus 4k. And to solve a quadratic, you want it all on one side, and you want to divide through by that -2 to get k squared where possible. So the -6 comes across and of course becomes a +6 on this side. And then once I divide it all by -2, it becomes k squared minus 2k minus 3. And we're going to get rid of that +6 there because we don't want to leave it in working and look like we've made an error. Solving this now becomes pretty straightforward. K minus 3, k plus 1. If you can't remember how to do that, look at my other video about how to factorize quadratics as a reminder. And then you finish up with -1 and 3. One thing I haven't done all the way down, you may have noticed, is I haven't put an inequality sign. But what I've done is I've solved for these two gradients being equal to each other. So I've just found the values of k which give me exactly the same gradient. I want every other option. So really all I need to do, and what I probably should have done to start with, is put inequality signs all the way down here. So what I'm finding essentially I'm finding that k cannot be -1 and cannot be 3 if the gradients are meant to be different. So every other value is okay. So I can say, therefore, for a unique solution, k can be all real values except, using our proper set notation, except for -1 and 3. And we can quickly check that if we want. If I put k equals 3 into this first gradient, you get 3 minus 2 in the denominator, which gives you 2. And on the other side, if you put -2 times by 3 over 3, that also gives you -2. And so notice that k equals 3 will give you the same gradient. We don't want that. We're getting rid of the k equals 3 solution. And if I do the same with -1, you'll find out you'll get exactly the same answer again. And we don't want that. So we are eliminating the issue with the same gradients by removing -1 and 3. Okay, that is case 1, where you have unique solution. Gradients cannot be the same. Case 2 is where you have no solution. So same gradient, different y-intercepts. So in this particular case, I've deliberately chosen exactly the same two equations so we can have the same setup of work, and then the finish is just that little bit different. So here, the first step, again, using this method, you can use other methods, is exactly the same. We still need to find out the gradient of each one, but this time, instead of putting them not equal to each other, I want to find out when the gradients are equal to each other. So instead of me repeating the whole process again, I'm just going to copy it down. But the difference this time is not that I want the inequality. I actually want the equal signs all the way down this time. So I'm going to remove all those. Because remember, case 2, so that I want the gradients to be equal. So I want I want them to be equal. That means they're going to be parallel, which with parallel lines, remember, it gives me the case of infinite or no solution. So if I get k equals -1 and k equals 3, it feels like, yep, I'm done. I've got parallel lines. That is true. This means parallel lines. But it doesn't necessarily mean no solutions. To find no solutions, also remember we had to look at the case where you had the gradients were equal, but the y-intercepts, whoops, I wrote not equal, sorry. So the gradients were equal, but the y-intercepts could not be equal. So now I must check the y-intercepts. So over here, these are our y-intercepts. Oh, I don't want to cut the letter off. That's C1 and that's C2. So essentially what I do now, you can see C2 is a constant. So we know we're going to solve or check, maybe I'll check rather than solve, I use that word. I'm going to check these values to see if you can make sure they're not the same. So we know C2 is going to be equal -5/3. That's a constant, that's not going to change. But C1, we know is 5 over k minus 2. So let's check that. When k equals 3, you find that C1 equals 5 over 3 minus 2. Because k is 3, you'll end up with 5. So when k equals 3, C1 does not equal C2. That's exactly what we want. So we know k equals 3 is a value that we want. And then we check k equals -1. So C1 will be 5 over -1 minus 2, and that gives you -5 over 3, which happens to equal C2. It's not what we want. Okay, so essentially what we're now saying is this is the only one that we want, because it not only makes the gradients to be the same, it also means my y-intercepts are different. So they can say, therefore, k equals 3 for no solutions. And to fit it, I'm just going to write that for solutions, a shortened version. So k equals 3 is our final result. But notice how it's all exactly the same working as the previous step for the first two sections. All the methods are the same. The only difference is having an equality sign, equal sign, instead of the inequality there, the unequal to sign, not equal to sign. And with that in mind, let's go to the final case. For our final case, I've chosen exactly the same equation once more. And really, all the working is exactly the same to get there. So it's actually really nice if you have a question where this steps it out, you can do one set of working for the first part for unique solution, and then you just tack on one more little section at the end for no solution or infinite solution. So really, you're not actually doing much extra work to get all the way to the end. So remember this final case. Gradients are equal and the y-intercepts are equal. So do we have a case where the gradients become the same and the y-intercept becomes the same? And the answer in this case is yes. Remember, we will go through, we'd find our equations as y equals. Then we solve our gradients equal to each other in our second step here. And we found that k equals -1 or 3, and that gives you parallel lines. Then we had to do one final check to see if we could have, in the previous example, we had one final check to see if we had different intercepts. This time I want them to be the same intercepts. And I've accidentally removed that 3 there. And we found, I'll give it that highlight if I can. When k equals 3, we had different intercepts, which was perfect for no solutions. But when we have infinite solutions, we have to have the same intercept. So k equals 3 is no good to us. So instead, we want to deal with k equals -1, because notice at the end k equals -1 gives you exactly the same intercept as the other one. Now this works even if you have a k. If you had a k in here, all you would do is you'd substitute your k value into both C1 and C2, into both of these, and you would see if they're equal to each other. That's how we're going to deal with anything where you asked for the number of solutions to simultaneous equations. Like I say, there are other ways to do it, but the methodology behind it is no longer in the Year 12 Methods course. It might change in future years, past 2020, who knows? But for now, that is how we're going to do our unique, no, and infinite solutions. Any more questions, please put them in the comments, and I hopefully we'll be able to answer them, but hopefully that is sufficient for you.